Hello, welcome to Triply 117, another week. Today we're going to talk about transformers and mutual inductance for this week, rather. The first thing I want to do was give you an high-level overhead view of the power grid. We've been talking a lot of math. Let's step back and tell you how the whole national grid is built to show you why we need these transformers everywhere. Okay, this is just another week that we're talking about pretty much power engineering. So let's talk about what is the U.S. national power grid, right? How far does it reach? For one, it reaches coast to coast. So it's West Coast is all the way here, East Coast is all the way there. This is an image of all the transmission lines in all of the United States, right? How big is the U.S. power grid? Several millions of miles of power lines, right? If you just look at the density on the west side, that's a lot of wire, and it will eventually add up to millions of miles of power lines. We have well over 7,000 generators sprinkled all over the United States, right? 400 million customers from East Coast to West Coast. Honestly, a lot of it's on the East Coast. So if you look at just the structure it's set up, people ask, well, why is the East Coast so dense? Because this is where the power grid was formed back in long 200 years ago or 150 years ago. The power grid actually started in New York City, and they started making pockets everywhere, and they started connecting between cities. Really, the East Coast started doing it first. Later on, the West Coast joined in, and then honestly, the Midwest is still kind of sparse, right? Now, the whole power grid is locked into 60 hertz, right? So that's just the grid itself. We all agreed in America, we're going to be running 60 hertz forever, pretty much. Yeah. That's why you always hear me talk about 60 hertz nonstop. That's what the power grid is. Okay. Now, within the power system, United States, all of power systems, but specifically United States power systems, there are three major categories of infrastructure. Okay, this is like the critical energy infrastructure is what we call it. In red, you'll have generation. So right here, you'll have a generation plant down here on the page, and then you have a step-up transformer. And this is what we're going to talk about today. Where are these transformers? So this red group is in charge of making electric energy or producing electric energy. So power plants, which is what this is, this building, it produces electric energy for the grid. Now, once it produces electric energy, it needs to travel a long distance to the customer eventually, right? Generation plants are typically built 50 miles, 100 miles away from major cities for safety reasons, and it's cheaper, and it won't bother people as much. So we need some type of, quote, interstate for the electricity to drive on, and that's your transmission system, right? So you have your transmission system in blue. These are your high voltage lines that transfer energy long between cities to cities, or the remote generation station to the major cities and customers. Now, once it gets closer to your neighborhood, you're going to have a third system called a distribution system, which will take your high voltage transmission lines, lower it to a more acceptable voltage, and then go down to individual streets, to individual neighborhoods, and eventually end up at your house, right? So that the power system will take energy from transmission system and deliver it to the customer. So three major groups we see in power generation. Okay. Now let's talk about all three of them one by one. Again, high level overhead view, no crazy mathematic details. This is what a generation station or power plant looks like, right? What devices within this plant will actually make electricity, right? It's called the generators. So the generators themselves are the ones that make the electricity. It's a lot of people think it's these giant cooling towers, this big smokestack. Those are the mechanical, chemical side of things. But somewhere around here, probably in this building on the lower left, there's an actual electric generator that gets spun. That's what produces electricity. Everything else in this plant is mechanical, fuel, all that is to produce the spinning energy for the generator to make electric energy. Okay. Where is this power plants typically located? They're far from residential areas because you don't want the pollution to come to you. You don't want the noise and the unsightly image of a power plant. So, given a chance, we try to build them as far as possible from residential areas. Other industrial customers could be close by, like refineries and everything, because they don't care, but definitely residential, far, far away. What are the typical voltage levels you'll see for generators themselves? So these generation plants, typically you're looking somewhere between 12.47 kV up to maybe 25 kV. You don't want to get too high of a voltage because then it's going to be more expensive to build the generators. So roughly about 10 to 20 something kV is the level you'd expect for generator voltages. Okay. Now, it's more efficient to transfer energy long distance the higher your voltage, right? So that's why we make these really high voltage power lines and span them 50 miles between cities, right? So how do we efficiently transfer energy from the generators to distribution grids? High voltage lines over long distance, right? Where do you typically see these? I'm sure you've seen these before, right? Driving around the interstate, you might see them going down I-5, on Howe Avenue across the river from Sac State. You'll see these in Elk Grove. You see them a lot, so they're everywhere. You just need to look up. But you'll notice if you're going to be electrical engineering, especially in the power industry, you're going to start noticing these more, and you'll see that they actually travel pretty far, roughly in a straight line, right? So these will go between cities, and they typically follow interstates, railways, or canals, right? Because it's easier to buy land near those things rather than buy land in a dense area, a residential area, right? So don't be surprised if you're going down I-5 and you see a transmission power line next to you, maybe like half a mile to your right, and you'll see it for like 40 miles, right? It's just following you. Electricity is following you down the line as you travel down south to Los Angeles. Okay. What are the typical voltage levels you see here? Typically 69 kV to 1 million volts. Now, there's a telltale sign to see. You'll eventually have a feeling of what voltage level these are. The taller the structure, the higher the lines are from the ground, the higher the voltage for safety reasons, right? So if you ever see two power lines closer to each other, the bigger, taller one tends to be the higher voltage ones than the others. Okay. I'm going to guess just looking at these are probably 115 kV or 230 kV lines. They're not 69, that's for sure. They're too high. They're too big for that. Most likely 230 kV be my guess. Okay. Now the third one is called distribution system, right? So once we get the electricity to the correct area, the city or the neighborhood, we need to transfer the energy to a low voltage level and eventually to your house, right? So we have a substation with a transformer, which will then feed voltage across these power lines, right? Now, who absorbs electric energy from the distribution grid? That's the customers. So this is a house right here. You'll see that off this little pole-mounted transformer, you'll have three wires that go to your metering pole right here. And then on the side of your house, about right there, you'll have an actual meter, and that's where they calculate how much electricity is flowing into your house, right? So customers, homeowners, residential, right? You might have commercial like Walmart's, banks, restaurants will have their own dedicated line off these distribution poles, and some light industrial applications like auto repair shop, or maybe like a small light like furniture manufacturing building, right? So this is called a distribution pole, and then you could see that you have power lines running through it, and then where do you typically see these? They're typically along the roads. So if you have like a major road between Sac State to Elk Grove or something, not the interstate, but like Power Inn Road or something, those major roads to your neighborhoods typically have these on the side, and they'll follow the road most likely. and then they'll branch off to neighborhoods. Or if you live in a fancy place and they paid extra money, they bury these underground so you don't have the unsightly view of the power line poles. All right. So if you live in Folsom area and in fancy houses, you're not going to see these because they paid extra money to underground it. Okay. What are the typical voltage levels you see on these lines? Lower limit is about 4.16 kV all the way up to 33 kV. I've never seen this high before, but there are the companies who use it. Roughly around here where I work at TID, we use 12.47 kV. I believe SMUD uses that as well, right? Some people keep talking about moving up to 25 kV class, or another popular one is 13.8 kV. So there's a couple of popular voltage classes here on the West Coast that we use. But for most part, know that this is lower voltage level than the transmission system. Okay, it's very similar to the generation side as well. So generation is kind of like 20-ish kV. Transmission jumps to about 100 kV because it's more efficient to send energy long distance. And then it goes back down to about a 20 kV level to then go to your house. That's typically what the system looks like. Okay, so talking about these jumping voltage levels, how can we interface that? Because you know from node analysis from circuits 1, you can't take 10 volts and 50 volts and put them on the same node. It's going to explode, right? So there needs to be a way to interface two voltages together efficiently, not just putting a bunch of resistors to make resistor division, right? That's a waste of energy. So we need a way to connect the generation grid to the transmission grid, and then the transmission grid to the distribution grid, go from that 20 kV to 100 kV back to 20 kV. We need these jumps. And we use a device called a transformer. This device has been invented about 100 something years ago. Very, very efficient. We've been using the same thing ever since, right? This is actually one of Faraday's first inventions and contributions to the electrical engineering community, right? So this device can link two different voltage levels together without blowing things up. That way, we can transfer electricity from one grid to another seamlessly, right? So here is the transformer in a substation. So this is typically will go from your 100 kV lines down to your 13 or 12.5 kV. And then this is your transformer on the pole in the front of your house. This will go from your voltages of maybe 12.47 kV up here to 120 volts coming out these terminals, and it goes directly to your house. Okay, so different levels of transformers, but they all work the same way. Okay. So I guess I would say history lesson here is in America, this transformer was actually a key component in winning the battle of AC versus DC with the Edison and Nikola Tesla, right? Man, I'm blanking out. So yeah. And the idea is back then there was no DC transformers. So the whole sending voltage long distance of DC was a terrible idea. AC was more efficient. And the transformer is what gave us the ability to change voltage levels easily. Okay. So if it wasn't for this transformer, we would probably be running a DC power system today. Right. So this is a critical invention in power engineering and electrical engineering as a whole. Okay. Okay. So let's talk about mutual inductance. Right. This is one of the key components that make transformers work. Now, here you have an AC power supply running current through a coil number 1. So what happens when current flows through a inductor or a coil of wire? You produce a magnetic field. So these loops with black arrows, these are field lines of the magnetic field being induced because of the current flowing. Okay, stronger the current, the stronger the magnetic field. If you have a second inductor nearby within physically close proximity, touching, right? it'll share the magnetic field. Some of it will get shared, not all of it, because you can see some of it goes in one side in the coil, some of it goes to the other. So a small portion of it will share the magnetic field. So what will end up happening is because the magnetic field is getting linked in the second coil, it'll actually induce a current and a voltage on a secondary circuit over here. So just by being in close proximity, two coils can link magnetic fields in between. And then you could get the electricity to, quote, jump a circuit, because these are electrically isolated. But the electric energy will jump through the magnetic field into the second circuit and then go to a load. And this mutual inductance, by taking two inductors and putting them close together, that's the key that creates this, that gives us the ability to make transformers. Okay. So a magnetic field is shared by a second coil, a winding, they call it winding, I call it coil, induces a voltage. This is your secondary voltage right here. And then your secondary current goes through, and there's a resistor here as a load. Okay. So a big takeaway is two inductors close by will share magnetic field, and then the energy will jump across the magnetic field to the second side. Okay. So let's talk about transformers. Let's use this property and change voltage levels. Okay. Well, we know what we could do construction-wise is we could take an winding, so take a bunch of wire and loop it around a giant iron core. This is how inductors are made. Okay. So you loop it over and over and over again, and then you get your primary coil. You make a big square piece of metal, iron, and on the other side, you can loop more wires to make a secondary coil. And then in between these is the metal iron core we built. Very, very heavy. Okay. Why do we have an iron core? The iron core is kind of a easy roadmap for the electromagnetic field to move. Technically, the electromagnetic field will operate in airspace, but having a giant piece of metal will help it conduct stronger and easier. So you'll get a stronger magnetic field traveling through the metal than you would just the open air. So that's why we have an iron core. Okay. So these two windings are now linked with a shared magnetic field. That's what this dotted red line is. It's a shared magnetic field. We're actually talking about right here. Okay. So we can have a certain amount of voltage on one side, and then it'll induce a magnetic field here on the left side, and it'll travel. The magnetic field will physically travel through the core to the secondary winding, and then another voltage will be induced, and then there'll be a load right here, and then you'll be able to power that load. Okay. So remember, the iron core is there to help link up the shared magnetic fields between the two coils. Okay. That way, the electric energy can be sent from one winding to another for AC systems with different voltage levels. Remember, we're talking about distribution. Generation is low voltage. Transmission is higher than distribution back to low. This idea of two coils with a magnetic field in between will help us link two separate voltages without blowing things up. Okay. Now, this principle is called Faraday's law of induction. You'll learn it in electromagnetic field for sure. But this pretty much, the shorthand Faraday's law of induction states that if you have AC voltage across a coil, it's going to induce a magnetic field. I mean, that's pretty much what it says, right? And then you just, with that property, we can link two inductors together, and then they'll share the field, and the secondary voltage will be induced as well. And that's literally how transformers operate, right? So Faraday was the first one to figure this out. Faraday's law of induction kind of came while he was making the transformer, right? So how do we control this, right? This, at the end of the day, we have this scientific principle, and we're looking at things and we say, okay, we could finally have some science we could put together and make a physical product to be useful. How do we manipulate it? Okay. Well, if the number of times we wrap the wire around the core, we could count, right? So we count the way I always do it, you should count how many times it loops on the inside. So it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So it loops 11 times. And I kind of try to count them one by one. So there's 11 loops here. On the other side, there's also 11 loops as well. So we could count how many times we wrap a whole loop around the wire, around the core with the wire, and we could say our number of turns is N. N is the number of turns. P stands for primary. Primary is just one side of the transformer. Okay. So the amount of wires on the primary side, primary is called, we say this, call it the left-hand side for today, is NP. The secondary side, you could count the number of turns there or number of loops. Loops and turns are the same thing. And you get NS equals 11. These are your secondary turns. So NP is your primary turns, number of what times we looped around the core. NS is the number of times we looped around the secondary side, which is the secondary turns, right? And we could figure out this ratio because that's going to have a direct impact on our voltage levels. And that ratio we could say is primary over secondary, NP over NS. This is called the turns ratio of a transformer. It's very, very important. In this particular one, we went 11 to 11, so it's equal to 1. But it's always going to be a ratio of how many windings on one side versus another. Okay. And this will give us our voltage control because we could change this NS to change the voltage level, right? And this we're going to show right here. So I like this image. It's a little more detailed to show you what would realistically happen. The previous one was just like a little textbook image. So here we have that giant iron core, so magnetic flux is flowing through it. Notice the primary windings, we wrapped it around many times. Look how many times we wrapped it around. So this is about 20 times we wrapped it. Okay. So let's do some little experimentation. If I put 20 volts across the red wire, and there's 20 turns, the way I think about it is each loop, I call this delta V. What's the voltage for one loop? Is 1 volt per turn. So we have 20 volts, 20 turns. I know every time I wrap it around, it's going to induce 1 volt per turn. And this magnetic field will carry that ratio, 1 volt over turn, throughout the whole field. So when you come on the secondary side, it's going to have that same 1 volt per turn ratio. Because that's remember, the magnetic field will link up the same voltage, will link up the magnetic field between the two coils. So on the secondary side, we only have 7 turns. But remember, it's 1 volt per turn. So then if we look at our secondary voltage, it's just 7 volts because there's 7 turns, right? So you see, by manipulating how many times we wrap around the wires, we could easily figure out what that voltage ratio we want, right? This is a 20 to 7 ratio. And if I want 20 to 5, I could just go in and just unravel 2 of these, and then I could get a 20 to 5 ratio, right? So it's just basically when you order inductors from a manufacturer, you tell them the exact ratio, and they're just going to go in there and just loop wires until they get that ratio for you, okay? So how do we use this? It's a very handy tactic for us that on the primary side, this ratio of VP over a volt over turn has to be equal as the same ratio on the right-hand side. So they're both the same ratios. Then we could just say VP over NP, which is 20 volts over 20 turns. That's going to be equal to the same ratio on the right-hand side, which is 7 volts over 7 turns. So this ratio must be equal at all times because the magnetic field the magnetic field can't induce or can't add or take out energy. It just passes energy through. So it's kind of like you can't destroy matter or decompose it. Same thing for energy. So this is a conservation law right here. Now, how can we use it for electrical circuits? Well, this ratio of primary voltage to secondary voltage, I could just say that's just primary turns over secondary turns. And this is in green. This is the corners, the the most key component of all transformers, is you choose how much of a voltage change you want, and then you choose this ratio of turns to accommodate that. So the design side is you choose NP and NS for the customer who states, I want these two voltages. Okay. Now that's for voltage. What about current? Because current's going to be flowing through the transformer just as much as voltage is, right? Voltage is induced across the windings. What about current? Well, we do similar idea. Let's say we have one current flowing through the red wire. That one current is going to loop 21 times, right? And so, and I think this one I put 20, I put 21. I just added one just to make the ratios easy. But so just pretend we opened it up and added one more winding, right? Just to make it easy. So you have 21 turns. So each current is going to loop 21 times. And every time we make a loop with 1 amp, it's going to add strength to the magnetic field. So magnetic field is the more times we loop an amp, the stronger and stronger it gets. So the way I like to think about it is after 1 amp went through all the turns, so we had 21 turns, I take 21 turns times 1 amp, I have 21 amp turns worth of magnetic field. Right? That's not the technical accurate way to say it. If you're taking electromagnetics, that professors probably shoot me in the face for saying this, but this is like the layman's easy way term to understand it. The more loops we have, the more current we flow, we multiply turns by current, and that's my total magnetic field flowing through. So I have 21 amp turns worth of magnetic field flowing through my core. We're not going to lose any of that. So on the right-hand side, we must have 21 amp turns to let go. If we put energy in through current, we got to take energy out through current, and they have to be equal. Conservation law. On the right-hand side, I only have 3 turns, or 7 turns. Well, I have 21 amp turns worth of energy to let out, so I must equally distribute the current through all 7 turns. I can't, now because it's one wire, a single wire is going through the entire loop through the entire core here, the blue wire. So one wire cannot change current. You can't have one loop have more current than another. At the end of the day, it's a single wire. So the current is equal for every single turn. And if I have 21 amps and I have 7 turns, I mean, math-wise, it's easy. Each loop is the current is 3 amps. So if I do my calculations, we'll have 3 amps and we have 7 turns. So it goes 3, 6, 9, 3, 6, 9, 12, so on and so on. I'll eventually get 21 amp turns. Okay, so notice with this, we had a change in current. We started with 1 amp on the red side, primary windings, 1 amp went in and 3 amps went out. Okay. So not only did we change the voltage, we changed the current as well. Right. And we could do this ratio again. Well, I know that to find the total magnetic flux flowing through, it's 21 amp turns. So I take the current times primary current times the primary winding. And that's my total magnetic field. This is equal to the same magnetic field on the secondary side, which is also amp turns, which is secondary amps times the turns ratio of the secondary winding, right? We kind of rearrange this to where you could get, again, a ratio of current in IP, primary current is what's flowing into the transformer versus what's flowing out, IS. And that's a ratio we can design for. And then the modifications we can do, again, is how many times we're going to loop the red wire, how many times we're going to loop the blue wire. We could always change this ratio NS over NP. This is from manufacturing standpoint. And that way we can have full control of the ratio current. So I could literally say if I have 10 amps flowing in, I want 50 amps flowing out, I could just make this a 1-to-5 ratio, right? So 2 major things is you got the voltage ratio and a current ratio. Those are the 2 bread and butter equations and principles that transformers operate off of, okay? So now let's talk about putting this into a circuit model, because previously those are the physical dimensions, okay? This is how you draw a transformer. You'll have 1 winding, and nearby, you should draw very close to each other, you should have a 2nd winding. And then you'll have these 4 terminals. So you have a terminal for the For positive primary winding, this is typically the positive terminal, and this will be the negative terminal down here for the primary side. This will be the secondary positive terminal, secondary negative terminal. Okay. Now remember, a transformer is just there to just let current through. It just passes energy through. It just changes the voltage for us. That's the main advantage. So we typically connect a power source to the primary side. So at least in the power engineering world, the primary side of a transformer is typically where the power is expected to come in. So primary is typically the source, right? The secondary winding is typically connected to the load. And then so current flows out the secondary winding. Okay. Now, with this setup, what type of equations do I need to solve for voltage and currents? Now remember, there's 4 voltages and currents. There's a VP for primary voltage. We got secondary voltage off this coil. We got current flowing into the primary side. We've got current flowing out to the secondary side. Okay. So the way I like to think about it is you could actually think of the secondary side. This is one loop where VS, this coil, is a new voltage source. So for the secondary side with a resistor, current, and voltage, I could use Ohm's law, V equals IR, to figure out my secondary voltage and current. But we're also going to need to know what jumps across the transformer. You have this NP over NS. So we have these voltage ratios. Primary voltage over secondary voltage is equal to NP over NS. It's a direct ratio. And for current, it's primary current over secondary current is the opposite of the ratio. So the secondary turns ratio is on top and the primary is on the bottom. The way I like to think about it is remember the voltage one because it's the direct primary to primary, secondary, secondary. So that's the easiest one to remember. And the current one, you just have to flip it. It's the inverse version of it. It's the opposite. Okay. So lots of talking, lots of equations. We need to do some an example to show you how the numbers work out. All right. So here we go. We have a transformer with a resistive load and a source. The voltage of the source is 120 volts RMS, angle 0 degrees. The resistor is 10 ohms. The ratio is 10 to 5. So NP is 10, NS is 5. Okay. So this turns ratio 10 over 5 is 2. So with that much, I should be able to solve and figure out all the voltage and currents in this system. So first thing I want to do is I need to figure out what VS is. If I want to find the current in all this loop, what's VS? Well, I have VP right here. I have the turns ratio NP over NS. So this is a direct substitution calculation, right? So VS is, you just look at the turns ratio. So remember, voltage ratio is VP over VS, so primary over secondary is equal to the turns ratio NP over NS. Primary voltage is 240 angle 0 degrees RMS. We don't know VS, so that's the variable we need to find. This is equal to 10 over 5, which is equal to 2. So to make VS must equal 120 angle 0 degrees to make sure that we have a ratio of 2 or 2 to 1. Okay, so immediately I know my voltage on the secondary side is now 120 volts angle 0 degrees. So with that, I could figure out IS because that's just Ohm's law. So I know my voltage, I know my resistance, find current, right? VS equals IS times R. Voltage of the secondary is 120 volts. We just figure it out. This is equal to IS, current flowing in, plus multiplied by the resistor at 10 ohms. And then you get IS equals 12 angle 0 degrees. So now you have your current on your secondary side. This is a current coming out the transformer. And we could backtrack to figure out the current flowing to the primary side right here. And that's another ratio. Current primary divided by current secondary, IP over IS, is equal to the opposite ratio, NS over NP. We need IP. We have IS, which is 12 angle 0 degrees. Our ratio is 5 over 10, which is 1/2. So then current is 6 angle 0 degrees. So it's less current. Okay. So a couple steps, but again, why do I like power engineering so much? This is arithmetic. I mean, that's all it is. Right? It's not that whole crazy integral, blah, 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 right? As long as you understand what each variable means, you understand how transformers operate, the math is pretty trivial. It's just knowing what to do when, right? All right. So with that being said, this is where we take our 15, 20-minute break to get exercise done in the middle of class so you can get some immediate work done and see how good you're understanding it. And then, get some feedback after 15 minutes because I'll show you how I did it. So just to go over here, we got the same circuit. This time, primary voltage is 480 volts, angle 0 degrees. The resistor is still 10 ohms. NP over NS is 100 over 5. So we have a lot more turns than before. See how this changes everything. Ideal transformer means you don't have to worry about any losses or any small power losses or voltage changes. It's all just straight. It's very straightforward. Okay. So kind of same process as here. Just keep on do the same thing with different numbers to get a feel for it. The second part here, it's a good question, is I didn't show you how to do this exactly, but I want you to use your engineering cap. What is the real power P coming off the resistor? You should be able to figure that out, right? You're going to have the voltage, you're going to have your current, you have VS, IS, you can find P for resistor, right? Real power P. Additionally, what's the real power coming out the source, right? You have VP, that's right there, 40 angle 0 degrees. You have IP, you can figure out the current and voltage coming out of this, right? So do that on your own. Remember what we learned last week about single phase power, and we'll come back and we'll check everything in a little bit. So good luck, and go ahead and pause this video, and we'll see you in a bit. Hello, welcome to EEE 117. We're back from our break for the Chapter 10 Transformers section. So here, which you can go ahead and see how we worked everything out. So remember, we have a transformer with a 480 volt primary with a phase shift of 0 degrees. R is equal to 10 ohms. Turns ratio NP over NS is 2. And we could go ahead and start solving everything. So first thing we could do is solve for secondary voltage because we have everything else. So VP over VS is equal to NP over NS. So you have 480 over VS is equal to 2. So voltage must be secondary voltage is equal to 240 angle 0 degrees, right? Number 2, so with VS, we could solve for IS. So VS equals IS times R. So we have 1 loop with the current. So it's just basic Ohm's law. So voltage is 240 is equal to IS times 10 ohms. So IS must equal to 24 angle 0 degrees amps. Okay, so now that we have the secondary current here, we could go back and find the primary current by working our way back. So here we have IP over IS equals NS over NP. We have secondary current, which is 24 amps. We just figure it out, angle 0 degrees. NS over NP is 50 over 100, so it's 1/2. Remember, the current is the inverse of the turns ratio. So primary current must be equal to 12 angle 0 degrees amps. Okay. The easiest way to tell, remember, if you're doing everything right, is if you see the primary voltage is really high, 480, and it goes down to 240, you must know the current's going to do the opposite, where you have 24 amps and it must go down to 12 amps on the primary side. So if voltage goes down across the coils, when you're going backwards, your voltage has to go down as well, right? Kind of crisscrossing. Okay. Because at the end of the day, what ends up happening is when we calculate the powers, we're going to have a secondary power side. So we're going to have voltage and current. We could do secondary powers VS, IS, cosine angle between the voltage and current. VS is 240 volts RMS. Current is 24 amps RMS. Cosine is 0 degrees minus 0 degree because it's just a resistor. There's no phase shift. This is gone. It's just 1. So our secondary power is 5.76 kW. Okay, notice on the primary side, we do the same thing with primary voltage is 480 volts RMS. Current is 12 amps RMS, and we get, again, 5.76 kW. So notice if you look at the ratios here, secondary side is 240 volts, primary side is 480, so it's a 2-to-1 ratio, but the current did the opposite. We went from 24 down to 12, right? And the more important thing is look at the power. They're the same on both sides, and that tells you something. Is that the power going through a transformer, or the power going in, must equal the power going out. Because the transformer itself does not absorb a lot of power. It's not a load, it's not a source. So it's just a pass-through device. Okay. So to make the powers equal, the voltage goes up a certain ratio, the current has to go down a certain ratio to make sure the power is equal on both sides. So that's why there's an inverse relationship between the change of voltage and current in a transformer. It's just physics at the end of the day. Okay. Excuse me. So kind of just talk about, let's put it in formally. How much power does entering the transformer primary side? 5.76 kW, that's P in. How much power is leaving the transformer on the secondary side? P out is 5.76 kW. What can we say about power in versus power out? They're equal. So very, very important part of transformers, P in is equal to P out. Ideally, there should be no power loss in the transformer. A lot of people make a mistake. Well, if my turns ratio is 2 to 1, that means my power must go down 2 to 1. Nope, power stays the same. Okay, the voltage goes down, current goes up, so the powers are equal at the end of the day. Right? Physics-wise is a very important concept. What it means is a transformer can't take energy out the system, nor can it put energy into the system. It's not a source, it's not a load, it's just a pass-through device. Okay? So that's like the three major parts of the transformer: voltage ratio, current ratio, and equal power. Now, let's talk about the turns ratio real quick. If you notice, we keep talking about NP over NS over and over and over again, but do we really care about the individual numbers of NP or NS? Not exactly. All we care about is the ratio at the end of the day. It's just the ratio that matters. So a lot of times in a transformer, we actually make it to where we just look at the ratio. We don't even draw NP and NS on a lot of diagrams in the power system. We just draw what the actual ratio it is itself. So you can either see a variable called A, which is a turns ratio, it's just NP over NS, or VP over VS, right? Or they just put the voltage. Like literally, you could just type, well, if VP is 69 kV and VS is 138 kV, with these two, I could figure out the ratio is 0.5, right? Because 69 divided by 138 is half. And there you go. That's your turns ratio. Okay, so main ways you can find the turns ratio is through the actual windings of both sides, not commonly drawn in circuit diagram on power system diagrams. Voltage ratio is very commonly drawn. We could just look at these two to find the turn ratio, or they could just give it to you directly, A equals 0.5. Okay, so just a lot of textbook, you'll have this A variable. Just remember that's just a turns ratio. Okay, and there's always VP over VS. Other more details about transformers, if you ever go buy a transformer, you'll encounter some of them are called air core and iron core. An air core transformer, the way you draw it in a circuit diagram, it's just two inductors near each other in close proximity with nothing between to represent the air gap, right? So air core is literally it's like taking two coils and just meshing them together. Or think about two springs and then we're kind of smushing them together on top of each other so that the magnetic field is shared between both of them, right? But there's no metal. So it literally, if you look through the coils, it's an air gap, right? The advantage of this is cheaper and less weight because you don't have to buy the metal. You're not spending money on the metal, which is it's probably the most expensive part of the transformer. And obviously without the metal, it's a lot lighter, right? The big disadvantage is without the iron core, you can't transfer as much energy. Because remember, the whole point of an iron core is it gives us more, the magnetic field is stronger in the iron core than it is in the air by a large, large margin. So the only time you ever see air core transformer is on very small power electronic devices, maybe like a little power supply for your computer or like your phone charger, where it's not that big of a deal. You don't need that much power. But in a large power system where you're pushing megawatts of energy, you definitely don't want to do this unless you absolutely have to, because you're wasting a lot of money. Even though it's cheaper, the power loss is so big that it's not worth it. Okay. Now, let's go to iron core, double star, because this is what we use in the power system all day long. The way you see in a circuit diagram is you'll see two double bars. The double bars represents the iron in the core, and they're wrapped around it. Right? Biggest advantage of it is a stronger magnetic field that can transfer more energy, right? So you get more bang for your buck out the transformer. The disadvantage is it physically costs more because you're adding a giant iron core in it, and iron's not exactly cheap, and the manufacturing process within it. And it's also heavier because again, you're adding a 1 or 2 tons of iron to it. It's going to be pretty darn heavy, right? And in terms of a power system, the heavier doesn't matter as much because we typically put them on the ground on concrete pad and we bolt them to the ground, so they're not going anywhere. right? In small electronic devices, this might be a big deal where you might want to use air core instead. I don't know. Other big issues with transformers is dot convention confusion. I hate textbooks that do this, but a lot of them do. They have different models of where the dots on the inductors go. Remember what the dot means? It's just if you look at the core, the winding, is it wound clockwise or counterclockwise? That's all the little dot means. From a manufacturing standpoint, we use a standard where we use the model B, where current goes in and current leaves the transformer. So current should always pass through the transformer. Current never doubles into the transformer because the transformer is not a load. So for example, this first model, you see how both currents are pointing in. Physically, this makes no sense because this I2 will always be going out the transformer every time. So by definition, I2 will always be negative. So then you have to put a negative on the equation, which already confuses people. Then when you go over here and then you put the dot on the wrong side, now you got to put a negative on the voltage because you're flipping polarity. And then when you put the dot on the wrong side and then you put the current out, now you're throwing more negatives. All this is again stupid and confusing. In power engineering or all engineering, we use keep it simple, stupid. So we're just going to use a model that's the cleanest with no modifications or equations. So part B is the best. This is what we've been using in this lecture so far. This is what I'm going to be using now on, where current flows in the transformer and then flows out the transformers. Both the dots are on the top. All your equations are just easy. There's no negatives everywhere. There's no reason to make this more confusing than it already is. Okay. And anybody, in my opinion, who tries to do these extra circuits, we're flopping the dots and see if you learn stuff, blah, blah, blah. It's a fruitless challenge because you'll never see these models A, C, and D in the world. This is stupid. No engineer will make it more complicated than it has to. So apart from a gotcha moment, there's no point in ever learning the other models, in my opinion. Okay, so kind of what's the best practice for dot convention? Let's go ahead and look at the transformer in detail. Current will always go into one dot and then will always leave their second dot. That's how I see it. So current into dot one will equal current going out of dot two. So remember, current just passes straight through the transformer every time. Okay. Don't make it more complicated than it has to be. Just pin this to the wall and just use this model every time. This is what the whole world uses. Okay. So just to summarize everything, we got a transformer is two coils close proximity overlapping with iron core to share the magnetic field between them. So two cores sharing the same magnetic field, right? Transformer equations, there's three of them. Vp over Vs equals Np over Ns. So that's your voltage equation. Current equation is the opposite, where you have Ip over Is equals Ns over Np. So notice that the turns ratio is flipped over for the current. Power has to go in. Power going in equals power going out for ideal transformer. It should never be sucking up a bunch of power. In real life, you might have 1 or 2% losses from the winding losses and just efficiency issues, but it should never be more than like 1 or 2%. So if you're getting like 20 or 50% difference, you're just doing the numbers wrong, in all honesty. Okay. For the model itself, just remember you're gonna have dot. If you even have the dots, current going into one dot equals current going out of one dot. That's the model we always use. So everything stays positive. There's no confusion. You have air core transformers and iron core transformers. Everybody in a power system uses iron core transformer because we need to have more capacity to get more power to flow through the transformer. Because all power systems is high power devices, right? Dot convention, just remember we just said it, current into one dot equals current out of the other dot. Okay. And that's pretty much all we have for transformers. So my goal here was to hopefully take a complicated circuit with lots of variables and dots and everything and try to make it easy for everybody, a little smaller, simpler models and bite-sized chunks that you have some idea what transformers are now, right? You're going to, again, if you're going to be in power system, you're going to see us again in 141, 130, 130, 142. It's going to be everywhere. Transformers are an integral part of power systems. So get a good base understanding right now, and as we add on more complications to it, if you understand this basic model here, it'll be a lot easier to understand as we get more and more into the magnetic fields and blah, blah, blah. Okay. So thank you for showing up. I hope you guys have a good rest of your week, and we'll always be here for the next lecture coming up. So you guys have a good day. See you around.